Simulations. Sometimes none of the preceding three approaches can be used. A simulation of a procedure is a process that behaves in the same way as the procedure itself, so that similar results are produced. Probabilities can sometimes be found by using a simulation. I want to do a relative probability. Relative probability is based on observations. But what if I want to know if I were to flip a coin 1 million times and I want to know how many heads and how many tails? Now, with our intuition, that's called subjective probability. Our intuition says we would have 500,000 heads, 500,000 tails, but we don't know. We want to simulate it. How would I do that? Well, I could write a computer program that actually flips a coin randomly 1 million times. I don't want to personally flip a coin 1 million times. We're going to simulate it. When you round probabilities, always read in Pearson underneath the answer. If they say to 3, do it to 3 significant digits. Please use what they say or you'll get it wrong. But in general, when we round probabilities, either give the exact fraction or decimal or round off final decimal results to 3 significant digits. For example, if I have 2/3, that is an exact fraction. If I want to turn it into a decimal, I would divide 2 by 3, which is equal to 0.666, and this is just repeating forever. Now, on your calculator, if you did this, you might have a 7 at the end. That's because it rounded the number of numbers you can have on your calculator. If I want to round it to 3 digits, I would say 0.667. If you don't know how to round, if I have 6, 6, 6, 6, and I want to round it to 3 digits, here's my third decimal place. I look 1 to the right. If this number is greater than or equal to 5, I round up. And if it's less than 5, eliminate numbers after the third digit. This is if I'm rounding to 3 digits. If I look here at my 6, if I look to the right, it's a 6. If it's a 6, that's greater than or equal to 5. I go back to the number before it, and I round it by saying 0.667, because I'm rounding up. This 6 becomes a 7. The same thing for 5/9. They are exact fractions, but when they turn into a decimal, they mostly repeat. Law of large numbers. As a procedure is repeated again and again, the relative frequency, remember, is an observation. My observed probability of an event tends to approach the actual probability. What that means, I'm going to flip a coin 4 times. I could get heads the first time, and then I flip it again. I could get a heads the second time. I flip it again. I could get a heads the third time. And I flip it again. I could get a heads the fourth time. Maybe the probability is small, but it's not impossible. Now, what if I flipped a coin 1 billion times? Now we're approaching large numbers. And the more I approach large numbers, the probability that I would get 1 billion heads if I flipped a coin 1 billion times is probably so close to 0 that we can call it 0. It's almost impossible that it's going to be a head every time. The more times we do things, the closer our observed value approaches our actual probability that we're expecting. Our relative frequency tends to approach the actual probability. I tossed a coin 1 billion times, I should get 500 million heads and 500 million tails. Caution, The law of large numbers applies to behaviors over a large number of trials, and it does not apply to any one individual outcome. Just because I flip a coin once, I still have a 50-50 chance of it being a head or a tail. But if I flip it twice, if I flip a head the first time, it's not that I'm going to get a tails the second. It could be a head the second time. That's because we're using small numbers. And when we're using small numbers, probability doesn't really kick in yet. It's just chance. If we know nothing, we should not assume things are equally likely unless we know they're equally likely. The actual probability depends on factors such as amount of preparation and difficulty of the test. There's many things that you could say there's this probability, but if each simple event in our sample space is not equally likely to occur, then we can't use our classic probability. Relative frequency. Relative frequency is, remember, observational. Find the probability of dying when making a skydiving jump. You don't have an equal chance of dying or living. I don't think many people would skydive if there was an equal chance of living or dying. We can't use classical. We can use intuition to say, I haven't heard of a lot of people who are skydiving who die, but there are a few. We could say it's very small. But we could also use our relative frequency, which says that we want the probability of dying when skydiving is going to equal the total number of outcomes, 3 million, that's in the denominator. And it's still living or dying. There's still only two possibilities, but only 21 people that I observed have died skydiving. I would say the probability is 21 over 3 million equals 7 times 10 to the minus 6, which would be the same as saying 7. And this minus 6 means I'm dividing by a million. I'm getting smaller, so I have to move my decimal to the left. 1, 2, 3, 4, 5, 6. Notice everywhere that I have one of these little scallopy things, I put a 0. That's my new probability. It's pretty small. And there we have it. And it just like we said, we have to use the relative frequency because we can only do observational. And here the classical approach cannot be used because the two outcomes, dying and surviving, are not equally likely. Let's do another one. In a study of US high school drivers, it was found that 3,785 texted while driving during the previous 30 days. I'm going to highlight the things that I want to remember. 3,785 texted and 4,720 did not text during the same period. And this looks like it's very official. We're going to assume that these are true figures. Based on these results, if a high school driver is randomly selected, find the probability that he or she texted while driving. We know the favorable outcomes, 3,785 students texted while driving. But we have to know the total that we're taking that from. We add 3,785 plus 4,720, and we get 8,505. And then we turn this into a probability by dividing 4, 4, 5, and I'm going to round it to 3 decimal places, and the next decimal place is a 0. I'm going to round to that. That is the same as 44.5%. So less than half, which makes sense because fewer students texted. Our interpretation is there is a 0.445 probability that if a high school driver is randomly selected, he or she texted while driving during the previous 30 days. It's a pretty big number. It's almost half. Thank you for watching.